Yeah, a little introduction about myself. My name is Andrea, and I work as a performance engineer for a company called Better Servers. We do cloud stuff, and my job is pretty much identify performance bottlenecks and try to make things faster when possible. And in this talk today, I would like to show you some profiling techniques that are usually used to do performance analysis, but from a different perspective, like using these tools to learn how the kernel works. So like spying what's going on in the system while your applications are running. And so why would you want to do that? Well, because often being aware of what the kernel is doing while your services or your applications are running can be very effective, not only from a performance perspective, but also to make your system more secure and more reliable. And I'm starting with with this statement that Linux kernel is complex. We have Jonathan Corbett here that before already talked about the complexity in terms of lines of code and how often the kernel changes. So being able to get into kernel development, even simply to understand what what a particular subsystem is doing, well, it's not trivial if you don't have the right tools. And yeah, this is one of the boring graphs that shows how many lines of code are in the Linux kernel. And well, we can see that lines are always going up. And like this one, I'm not sure if you're familiar with this one. It's a fractal-like image. It's a graphical representation of the source code in Linux. And it's already complex, and this was an old kernel at 2.4, and now in 2.4 we had like 2.5 million lines of code, and today we have like more than 20 million lines of code. So it's not something that if you need to understand something in the kernel, it's not that you just open the source code and you just can read everything. And in addition to that, not sure if you can read this slide, but in addition to that, Linux code is changing a lot. Like this graph shows every kernel release, how many patches we have. And we can see that like pretty much every 2 months there's a new kernel release, and every release is getting from 12,000 to well, almost 15,000 patches. So not lines of code, but logical patches. And that's a lot. It means even if you are able to like study the kernel today, if you look at the source code after 2 months or 3 months or later, all your keeps are changing. So it's difficult to keep up with all these changes. So how to keep up with these changes? Well, I'm pointing you to these sources. One is Linux Weekly News, is great. They do like a periodical report of what's going on in the kernel community. Very well done. It's a really good disclosure, so I recommend you to subscribe to that. We have John. And the other one is kernelnewbies.org/Linux changes, and this website bring you to a page. It's a wiki page, and they do like every kernel release, they create a new wiki page with all the most important features, and at the very top, and then all the other features that are added in or changes that are added in with a link usually to the commit or the patches. And so despite the name, because the first time that I saw kernel newbies, I was like, well, no, I don't need that, not a newbie. But instead, they do a very detailed report of what's going on in the kernel. And the next one is the kernel mailing list. Even if I'm not recommending you to subscribe to the Linux kernel mailing list, unless you really want to get into kernel development, because the volume is huge. There's like, I don't know, probably 200, 300 emails per day. So it's a good source to understand, I mean, to get into kernel development, but you need to spend a lot of time to follow everything. And the last one is the documentation folder in the kernel source code. And I think today is the best documentation that we have. I mean, it's a bunch of text files, but it's the best way, I think, to keep up with a project that is changing so frequently. So usually when you're searching for something in particular, taking a look at the documentation folder, even with a grep, something simple like that can solve you your problem. So fine, we've said Linux kernel is complex to understand. There are some sources, some documentation that you can look at. But yeah, today I want to bring you an idea, like what about using real-time tracing tools to inspect what the kernel is doing? So using these tools that are usually used for performance tracking as tools to learn the kernel. And so yeah, I was trying to show you the easiest way to trace something in Linux, and I was thinking of ftrace. Not sure if you're familiar with any other tracing tools. I think everybody knows about ftrace. It's the easiest way to trace system calls. So you're not tracing everything in the system, but it's focused at system calls. And I think all distributions are shipping ftrace. Even my phone, I cross-compiled ftrace and copied into my phone. And yeah, so ftrace is an easy way to debug system calls, meaning that when a user space process needs to communicate something with the kernel, it's doing a system call. And ftrace is basically adding a breakpoint to each system call. So when the process is executing a system call, you can see the output and with all the parameters passed to the system call, and also the return code. Because what it's doing is that it's setting via ftrace, it's setting a breakpoint at the beginning of the system call and another breakpoint at the end, so that you can also get the result. Now, sure, ftrace is it's everywhere, it's easy to use, but it's limited because its scope is only system calls. And another problem, so basically you don't see what's going on behind the system call, what the kernel is doing on a functional level, while you can see what your application is doing at the functional level using something like GDB, for example, or any other debugger. Another problem with ftrace is overhead, because these breakpoints are adding sometimes a consistent overhead. For example, when I talk about ftrace, I'm always showing this example I ran this like yesterday on my laptop and copied the output. The first one here is a DD, basic DD that is reading from dev0 and it's writing to dev null with a block size of 1 and a count of 500k. So this command is doing like 500k reads from dev0, 500k writes to dev null. And so it's a total of 1 million system calls. You may think it's taking a while to run, but instead it's just taking 0.5 seconds. However, if I run this same command inside the ftrace, and I'm even tracing a system call that is never called, like except the socket system call, In this case, same command is taking 44 seconds. So it's about 88 times slower than the original command. So obviously, when you think like, oh, I have an application in or a service in production, I want to see what it's doing. Oh, sure, let's just strace and attach to the PID. Well, you may affect its behavior a lot because you're you're adding a lot of overhead if you do this in production. In fact, sometimes I'm worried to run strace in production because of this. Especially in servers, like if you have web servers or stuff like that. So there must be a better way to do, like, to trace and not just strace or the basic command, this basic command. And what I would like to show you is BPF or eBPF. This is, by the way, this is the logo. I don't know why it's a pony. I think because the trace started this craziness with with a pony, and now other tracing tools are following this policy. Or I'm not sure if it was the trace or another tracing tool, but anyway. My wife thought I was talking about kids show or something like that when she saw the slides, but. BPF, so if you were in the other room with Jonathan before, did a very good disclosure about eBPF, what it is. It's basically a virtual machine that lives inside the kernel, and it can be programmed from user space. So you can basically inject kernel code from a user space program, and this code can be, I mean, you can use BPF for many things. I'm focusing at the tracing part. So BPF, you can attach code to a kernel function and run a BPF filter. So what you can do, you can basically run kernel code to do tracing. And the advantage of using BPF is that it runs in a secure sandbox. So there's no way, obviously assuming there are no bugs, there's no way to break the system with your code. You can break the system if there's a bug in BPF, of course, but your code is totally safe. You can do anything. And if there's a problem, your code simply it's not loaded at all because there's an in-kernel verifier. So I'm not gonna, I mean, there are many other documentation and talks about that are explaining what BPF is. I'm going fast in this part. Basically, it all started with BPF stands for Berkeley Packet Filter. It was a networking thing to do fast filtering for network packets. And the idea was to program, filters, like totally generic filters, and translate into code so that you receive a packet as an input, and you run this program, passing the packet as input, and depending on the result, you determine if you can accept or refuse the packet. Actually, I'm going to show you something that probably clarifies this. Let me run, for example, TCP dump. You see that? Yeah. Host, localhost, and port 22 and TCP. So, for example, here I'm tracing all the packets that are coming from on this host, on this laptop, on port 22, and protocol is TCP. Fine. You're probably familiar with this tool. This is a network monitoring tool. Now, even passing -d, do you know what it's doing? Anybody? So if I'm passing -d, it's showing this assembly. And yeah, I'm not going to tell you, this is not x86-64. Let's put this here. But it's actually a eBPF assembly. So what TCP dump is doing is converting this into this following code and injecting this code into the eBPF VM. So when a packet is received, this code runs. And for example, if you see the first instruction, we have a load at offset 14. This is loading. I mean, the beginning is the beginning of the packet. So it's loading data from the packet. What's the advantage of this for TCP dump? The huge advantage is that this code runs in kernel, not in user space. So you don't have to copy all the packets from kernel space to user space, but you apply the filter to the kernel buffer directly. And for example, in this case, only if the filter at the end returns 0 or 1, it depends. It means that the packet has been accepted, and only in that case you perform the copy from kernel space to user space. This is great because you can save a lot. Otherwise, the alternative would be to like either copy all the packets that you receive to user space and apply the filter in user space. That would be, I mean, really a really huge overhead. Or either write a specialized kernel module that does what you want to do with your filter, but writing kernel code has all the downsides of, you know, like you potentially can break the system because, yeah, you have bugs, like you have a null pointer to the reference and you may crash the system, or you exceed the stack, and yeah, crazy things can happen, like memory corruptions or even file system corruptions, stuff like that. So this one is a really powerful feature. And so it started with networking, but more subsystems in the kernel are converging to eBPF, are using eBPF for other purposes. For example, tracing. Instead of accepting packets as input, you may think you can accept like a dump of the CPU registers instead of packets, and you can use that to, I mean, you can apply your filter to a CPU state and do tracing, or you can use BPF with seccomp. If you're not familiar with seccomp, is you can see it as like a firewall of system calls. That is also a feature. I mean, using seccomp with BPF has been added recently. So now with a fairly recent kernel, you can program you can define seccomp filters as BPF filters. All right. So yeah, there are many usage of eBPF. Now I'm going to focus at the last one, observability. You can do many things like DDoS mitigation, intrusion detection, a lot of security-related stuff. And the other piece that I need to show you, then I can show you some examples because you know the lunchtime is approaching and the attention is. So yeah, the other piece that is missing is kprobe, but I mean, it can also be Linux tracing events or other things, but I would like to show you kprobe. Kprobe is another feature in the kernel. What I'm talking about, it's all mainline kernel. I'm not talking about other external patches or out of tree patches. Kprobe has been in the Linux kernel for a long time, and basically you can rewrite like binary patch. Binary replace any instruction in the kernel, but I should rather say any function in the kernel by replacing like the first instruction with a trap. So when the function is called, you can redirect the execution or hijack the execution to a custom handler. And then when the custom handler is executed, you single step instruction 2, then you return. And so it's all transparent to the called function. And you can, you can basically hijack your own kernel code when a function is called. This is great because if the handler it's BPF, we can intercept any kernel function, run a BPF filter or BPF code when the function is called, and do whatever we want. Because BPF is nothing less than kernel code with some restrictions, of course, but it's still kernel code. So that you can access kernel structures, and yeah, you can do all kind of inspection that you want. Obviously, you don't have to do all of this manually. Like you don't have to write bytecode manually or inject the code with a crazy mechanism like it ultimately it's a system call. You configure a BPF filter by doing a system call that's called BPF. But there are better ways to do this, and there are front ends. I'm gonna show you this one because it's the one that I'm more familiar with. There's another called Ply. This one is great, I think, because it's it started with Brendan Gregg. It worked. It wrote like all the basic tools and everything, and now it's maintained by iVisor. They're doing really good things. And the BCC stands for BPF Compiler Collection. It's basically a front end to BPF. That means that that there are bindings in C, Python, and there's I mean, it makes use of Clang LLVM to compile your BPF code and generate the bytecode. So basically, what I mean is that you can write, for example, your BPF code in Python, even if the code, the filter, the BPF filter itself, it's still in C. But you can embed the C code into your Python program. So when you run this Python program, it automatically compiles the C code and injects the code into the kernel in BPF. And but it's easy. I mean, I'll show you. It's there's. I would like to mention also this other project that's Go BPF. And there are bindings to BPF in Go, so you can write your BPF tool or BPF command or BPF filter in Go. And let me show you an example. So BCC, I think it's also shipped like in Ubuntu, for example, or Fedora for sure, I think. But you can download, you can get the source code on GitHub, and it's really easy to compile. There's a detailed guide. And for example, let's see, I'm picking a tool like this func count. It's a Python program. So it's all Python. And yeah, for example, here you can see that the filter itself, it's written in C. And then you can, so it creates this BPF text that contains the C code. And then it's probably passing this BPF text to a Python class that is called BPF, if I remember correctly. Yes, exactly. And this is all you need to do to write a BPF tool. Now, I would say that like 90% of the times you don't have to code at all, because in addition to this library, BCC includes many tools. Like, let's see, there's a lot of tools where you can trace whatever you want. For example, this one func count that I showed you is you can pass as argument a regular expression, and it's counting how many times the kernel is calling every functions that are matching that expression. So yeah, it's really nice. So yeah, let's see some examples, because this was the theoretical part. I'm gonna skip this one, and I'm gonna do this because I think it's more interesting. Then we can go back if there's time. Let's pretend that I want to identify where and how keyboard, well, characters, I should say keyboard events are received and processed by the kernel. And let's also pretend that I don't know anything about the kernel itself. That's very, yeah, let's do that. So the only thing that I know is that, let's say I have the source code here. I just did a git clone of the latest Linux source. And I have BCC down here. And I also have like a minimal understanding of how computer works. So the very first thing, how would you do that? How would you approach that? And for sure, the keyboard events are probably interrupts, right? Because it's unlikely that the CPU is polling constantly for me pressing a key on my keyboard. So what I can do is to use the fun count tool that I showed you before, and do something like this, like interrupt star interrupt star. What I'm doing here is that I'm programming BPF and using, actually I'm using kprobe to attach a BPF filter to any function in the kernel that are matching interrupt, that have interrupt in their name. And then I run a BPF filter that is simply incrementing a counter every time that a function is executed. So if I run this, yeah, it's obviously it's failing to attach the filter to some special functions, but let's ignore that for now. Now let me try to, I don't know, press some random keys on my keyboard, and then I can stop with Ctrl+C. And as you can see, I mean, I was able, like with a single command, without being worried to break my system, and without being worried of adding too much overhead to the system, because this is all kernel code with a simple counter, I was able to trace all the interrupts, or better, all the functions called something interrupt, something else, and it's likely to be all interrupts in my system. And I can see, I don't know, what is it? This is timer interrupt. This is the Wi-Fi. Yeah, the graphic related interrupt, USB. And yeah, look at that. This is AT KBD interrupt. This looks like a keyboard interrupt, right? So, well, in addition to that, I mean, there's 164 interrupts. I didn't press 164 keys, but that's because there's probably something else going on. I mean, I can receive other interrupts for the keyboard. So now the next step is to use another tool called trace, because I want to inspect. I'm going to go further and understand more about ATKBD, what it's doing. So I can do two things, actually. One thing is to go straight to the source code and search the function and see how it's implemented. And so let's just do that first. To find the function, I'm actually using ctags. There's also cscope is another tool. Who is familiar with ctags? Few? Well, basically, what it's doing is, especially in the kernel, you run make tags. There's an entry in the make file that is calling ctags, and it's creating a file called, let's do this, called the tags that contains a mapping of all the symbols, and it's pointing to the file and line number where the symbol is defined. So with this index, you can basically use VI and jump to any function or structure. So in this case, I was looking for ATKBD underscore interrupt. I can just do a colon tag ATKBD interrupt, and it brings me to the implementation of this function. So yeah, I see that this function is getting like 3 arguments. One is a structure that probably represents the device. Second argument is data that looks interesting because it's likely to be the scan code of the key that I'm pressing or something related to the keyboard events. And then there's flags, that is another argument. So let's make sure that AT keyboard is actually the function that I'm looking for. I can do this. I can use trace. Trace is a tool that where I can pass a symbol here, a function name here, and it showing me live every time that this function is called. So probably now that the filter is running, if I press something on my key, for example, I press J, yeah, I see that this function is called when I press the key. But I want to see more, like, let me do this. I'm passing the prototype of the function down here. And there's also signed into flags. So I can pass the prototype of the function, and now I can access to the arguments. So for example, let's say I want to see as a percentage x, so as an x number, I want to see data. Yeah, okay, there's a warning because it doesn't know what struct CRIO is. So I can, oh, look at that. It's already, you see, it's already printing something when I press the keys. If I want to suppress the warning, I can just go here and search for CRIO. That is likely to find here. So this is CRIO, and the file where it's defined, it's an include file. So I can do like -i, this include, well, actually it's not here, but it's my home. Linux include, fine. And now I can also access the CRIO information. For example, there's a one here that looks interesting. It's a char name. It's likely to be the name of the device. So let's add also this, like device %s and data, or CHR equal this. And I need to pass CRIO, pointer, name, and data. All right. Well, we got another warning, but let's ignore that for now. So let's see what happens. Oh, this is amazing. Now I can see the particular device that got the event, the interrupt. This case is a IE8042 keyboard port, whatever, and I get an X number. Actually, check this out. If let's say now I'm pressing J, and I keep J pressed. As you can see, I'm getting scan code 24 in X. When I release the key, I get A4. So what do you think about that? Well, basically, what I have is that I'm getting an interrupt every time that I press a key, and I'm getting another interrupt when I release the key with a different scan code. And if you pay attention to the number, A4, it's basically 24 with the most significant bit set. So the most significant bit determines when the key is pressed or released. So, and now at this point, we're done. Basically, if I write all these scan codes and dump those to a file, I already found a way to write a keylogger. And without knowing anything about the kernel, I was able to hijack an interrupt routine in an efficient way, in a fast way, totally transparent way, and without risking to break the kernel. So yeah, we have time. So I can show you. I prepared other examples, and this one, I'm going to show you this one because it's easy and I think it's really effective. There's actually a dedicated tool to do this, like trace all the exact system calls in the system. because we are in the security track, and I think it's for a security perspective. I found that sometimes it's really helpful to be able to see what is executed on the system, like having a system-wide view. Because usually, I mean, you can trace a process or a group of processes, but being able to trace all the exact system calls in the system is really useful when you're trying to do hardening on a specific server, because you may find that something is run when you were not aware of. To do that, it's really easy. We can just use trace as before, and so what I need, let me show you this. What I need is the exact system call. Let's follow the same approach that we were following before. Like, let's pretend we don't know anything about the kernel. But I may guess that the exact system call is called exec, right? So again, func count. Let's do exec. And let's see, let me run some programs here, dms, ps, ls, whatever. And Ctrl-C, break. All right, I got this one that looks interesting, x86 underscore sys exec v. I got ACPI that are probably not interesting. There's this one that is also interesting with this weird suffix, and this is something that happens, I think, with recent compilers, GCC compilers. It's there's this name mangling when a function is cloned multiple times. It's adding this symbol. I don't know exactly why. Maybe we should investigate. But yeah, let's actually try to trace this function. Or better, let's see in the kernel source code what this function, how this function is, what this function looks like. And it's a doexecv file that is called by this doexecv at common and many other functions. So yeah, let's say. As you can see, there are many arguments also here. So I can do the same trace trick and attach to this function. And yeah, let me pass just the first two arguments, because you don't need to define everything, to define all arguments if you don't need them. And this. All right. Yeah, it's failing because it's expecting to this name, not doexecv file. This is a mismatch between the function name defined in the source code and the function name for the tracer because of how GCC compiles the code. So I can do something tricky like this, and that should work. All right. Let's do, I don't know, ls. Yeah, so every time now in the system, not only from this shell, but everywhere in the system, every time that a process is executed, it's telling me which process ID and process thread ID and command executed that file. And as you can see, independently on the command that I'm running, I'm always getting bash, because bash is the one that is executing the file. If I want to see what command is executed, I need to inspect the arguments. And the arguments were like, let's go back to the source code. I need to inspect the, I likely need to inspect this file name, because it looks like the argument that is executed. So file name, let's see where it's defined. Here, 13. Oh, nice. File name as an attribute called name. And so if I'm, and it's a string. So if I do %s file name pointer name, let's see what we get. Right, traces, the filter is loaded. Now, oh, look at that. PS, ls. Now, in addition to the program that is forking, I get also the program that has been executed. So this simple command allows me to trace all the programs that are executed in the system. Like I was saying before, this is useful when you try to do hardening for a box and you want to make sure that no other services that you're not aware of are running. So yeah, simply by looking what's going on in the system, you can do this. We have, like, we're running short on time. Yeah, 20 seconds, I'm gonna show you this, and then I'm done when we do questions. So there's another tool. I'm not gonna show you a demo, but I just wanna mention this. There's a tool that allows to even trace when a program goes to sleep and when another thread is waking up that sleeping thread. You can connect these two and get this nice stack trace of a program that is going to sleep and the one that wakes up the sleeping thread. This is really I find this really useful, especially for embedded development, because usually when you do embedded stuff, you have a program that is sleeping on some events, and it's really, really difficult to find who and when the process is resumed from its execution. So yeah, let's end here. You know already the conclusion. I wanted to give you the idea of using tracing tools as methodology to study the kernel. I added some references, and yeah, I guess I'm done. If you have questions.
Thanks, Andrea. Just we have the time just for 1 or 2 questions. Okay.
Yeah. So, sorry, what? Oh, the ping exam.
Well, we have another question, sorry.
So, basically, what's the difference these days, if there is still some difference between what is ftrace and eBPF?
And eBPF.
I guess
yes,
eBPF is even more flexible because you can, but are there other differences, like, I don't know, overhead or?
Yeah, ftrace. I mean, ftrace has been in the kernel since forever. I think I started to do kernel stuff in 2004, and I think ftrace was there even then. Probably not, but a couple of years later, so if that wasn't the year, ftrace was there. Ftrace allows you to catch when a function is called, but then you don't have the whole flexibility that eBPF gives you, because eBPF is a totally programmable machine that you have in addition. It's like having another CPU that runs in a system that can access whatever the kernel can access. You know, it's probably ugly to say that, but you can think at eBPF as the JavaScript of the kernel, because it is what it is. You know, you can compile bytecode and inject the bytecode in the kernel without being worried of breaking things. I actually, a long time ago, I actually wrote a kernel module that was using ftrace. No, it was kprobe, not ftrace, but you know, it's pretty much the same. It was using kprobe, and it was it had some special custom code to do profiling. The problem is that I passed my code to one of my coworkers, and it introduced a pretty nasty bugs because it was started to use a stack bigger than 8K. As you probably know, you have a limited amount of stack in the kernel, and if you're exceeding the stack, yeah, nasty things could happen. And what was happening was that it corrupted the root file system everywhere in the data center. That's you know, that was pretty big. I learned on my skin what means shipping kernel code that is not tested enough. With eBPF, I mean, you don't have to be worried about that. Just so that's a big advantage.
Another one? Okay.
Do you think that eBPF can go beyond the simple tracing and could also be used, for example, for some monitoring or auditing of security? Or
Yeah, it's actually already going beyond what I what I showed. Like I was saying, many other subsystems are making. I'm changing to be based on to be on top of eBPF. Like seccomp is one. There's even the infrared device drivers. Like Jonathan was saying in his presentation, every infrared device has its own protocol. So to support all of them, you either need to ship a lot of code that supports everything, or you can define the encoding as an eBPF filter and inject the code only specific for the device that you need. In the future, I mean, there are predictions for this future. Some people are saying that eBPF will be a replacement for all the binary blob that usually runs in your system, like a firmware for a Wi-Fi card, or I don't know, a network binary blob that you load in your kernel. That is a black box, but that can be a BPF filter. So that's an interesting topic. I mean, people are using. I think BPF is one of the hot topics today in the kernel community.
Well, thank you, Andrea,
Right.
for your very good presentation.